Well, it's been more than a week since I left off with this stuff, so maybe you possibly have forgotten one or two little bits of it. Let me just kind of summarize the last few minutes of whenever it was we were looking at this before. The last thing that I've gotten to is Kirchhoff's laws, of which there were two. It follows, first of all, from conservation of energy, because the loop rule is about voltage, and voltage is energy per unit charge. So it follows from conservation of energy that if you go around a complete loop in a circuit under steady, unchanging conditions, that the total of all the changes in voltage have to add up to zero. If increases are positive and decreases are negative, you have to, when you get back to the point where you started, it's going to be the same potential there that it was when you left, the same voltage. And so the changes going along that loop have to balance each other out. In order to use that to write an equation, you have to have a good idea of which end of something like a battery is higher than which. So I put a couple of pictures there in the middle of whatever page number that is, 15, I guess. A battery, the symbol is that little thing there. And actually, I believe I put these on the formula sheet with the plus. You don't normally see the plus and minus signs when you're looking at a wiring diagram, but on your formula sheet, I put the plus and minus next to it just to help you out a little bit. But one way to remember it maybe is just that the bigger side of the symbol is where you have the bigger voltage. Positive is the higher potential side of the battery. For a resistor, to know which end is positive and which end is negative, you have to know what direction the current flows through it. Current flows from high to low potential. This being conventional positive current, flows from high to low voltage, the same way that water flows from high to low elevation. So with those things in mind, you can add up all the voltages around a closed loop, and just about today's whole class is going to be examples illustrating this, but that's the loop rule. The point rule follows from conservation of electric charge. The point rule deals with current, amps in other words. Current is charge per unit time. And if you have a point, such as a junction, some books call it the junction rule rather than the point rule. Since there's no way to store charge at a point, the rate that it flows into that point has to equal the rate that it flows away from that point again. And so total current in equals total current out. So for example, let's say you've got a 10 ohm resistor in series with a 20 ohm resistor, and the question is to find the current flowing through this circuit. Now, probably the easiest way to solve this actually is to have the idea of equivalent resistance in mind and say that a 10 and a 20 in series is equivalent to a 30, and you stick the 30 ohms together with the voltage into Ohm's law, and that would be a good way to do it. But I'm going to approach it with Kirchhoff's loop rule. Well, for one thing, that's how you go about proving that equivalent resistance adds up like that. Plus, a fairly simple example as sort of a warm-up for more sophisticated things where you can't just do it by determining equivalent resistance. So, number 2. The question doesn't come with a picture. I would draw one so I can label some stuff on it. Plus, it's just good to be able to look at what you're dealing with. So we have some kind of a source of EMF, such as a battery. Incidentally, those of you who got here after I passed the papers back, I've got your tests done, so stop on your way out. I'll get that back to you. Two resistors in series, 10 ohms, 20 ohms. The current would flow around the circuit in that direction because current, conventional positive current, flows from plus to minus. Positive charges would be repelled by the positive side of the battery. They'd be attracted to the negative side of the battery. So plus to minus. And the potential difference across the first resistor, I'll call delta V1. The voltage across the second resistor, I'll call delta V2. The loop rule says that if I start anywhere and go around this loop, the voltages add up to 0. So I'm going to start here at the lower left-hand corner for no particularly good reason. It's just as good a spot to start as any. And I'm going to go around clockwise, again, not for any particularly good reason. It's just as easy and just as correct if you go around the loop in the other direction. But if I start here and start going that way, normally you assume the wires to be at a constant potential. Real world, especially if the currents are large, you might lose a fraction of a volt between one end of a wire and the other, but well, you know, it's like the frictionless surfaces that we have in physics 131. Not quite true, but usually a good approximation. And resistanceless wires would be something in the same category. So anyhow, no voltage change as you move along the wire until you get to the battery. As you cross the battery, kind of tracing the diagram with your finger, you go from the low side to the high side. So that's an increase. And I'll fill in numbers in a minute, but I want to keep it in symbols for a couple of lines, just because I want to make a general point here. Positive because it's an increase, and E for the EMF, that stands for the 1.5 volts. Well, you continue following the loop, and no change as you go along this wire until you get to the first resistor. The loop takes you from the upstream end to the downstream end. That would be a decrease in potential. Decreases get a minus sign. From there, the next thing you get to is the second resistor. Again, as you follow the loop, you're going from the upstream end to the downstream end. That's another decrease in potential. From there, I can get back to my starting point without any further changes. So, summation of the voltages around a complete loop is 0. Well, the question asked for the current, and the loop rule is about voltage. The way you can bring the current into it is with Ohm's law. Each of these delta V's is equal to I times R. Voltage across a resistor is I times R. So I added the delta V's to both sides while I was at it. In a series circuit, the current is the same everywhere. Remember, current means the rate of flow. If you want to compare it to cars going down a highway, well, if you've got 30 cars per hour going by this point, you've got to have 30 cars per hour going by that point, 30 cars per hour going by that point, because there's no place in between for any of the cars to go. Coulombs per second through a wire, cars per hour going down a road, same general idea. So same current I don't need any subscript on that. Well, I is a common factor. I can factor it out. Over here. Here's the point where I demonstrate the formula for equivalent resistance, which a week or two ago, I basically stood here and said, trust me, I'm a professional. Well, now I no longer have to appeal to personal authority. This is how you prove that R equivalent equals R1 plus R2. If there was a single resistor, this would be volts equals amps times ohms. The resistance of that one resistor would be where this quantity in parentheses is. And probably you can see that it would be a minor variation on the same argument if there was 17 resistors instead of 2 of them. You would just have a delta V3 and a delta V4 and a delta V5. And so you'd have all these IR terms, and you factor out the I, and you'd have R1 plus R2 plus R3 plus R4. So notice that equivalent resistance in a series circuit, equivalent resistance in a series circuit is the sum of the individual resistors, as asserted without proof previously. Well, having gotten that out of the way, let's stick the actual numbers in and get the answer. For this particular problem, EMF is the 1.5 volts. I is the unknown. The two resistors are 10 and 20. Let's see, probably looks better. So 50 milliamps, 0.05 of an amp. And just a little footnote to that. I already said this a minute ago, but when I was back over here first drawing my drawing, I said that I was going to go around the picture clockwise, but you could just as easily and just as correctly go around counterclockwise. It makes no difference. If I started here and went around counterclockwise, you'd go down across the battery, and then you would cross the resistors going from the downstream end to the upstream end, which would be increases in potential. And you get what amounts to the same equation, except it's been multiplied through by -1, which has no effect on how the answer comes out. So how do you know which way to go around? You flip a coin because it makes no difference. Clockwise or counterclockwise, pick your favorite. Number 3. Kind of a similar question to number 2 once you get into the guts of it, but it's there to illustrate the idea of internal resistance, like already came up in one of the labs. And we're talking here about the internal resistance of a battery, but anything, realistically, anything that has a current flowing through it has got some internal resistance. A coil, or just simply the wires that connect things. Unless you want to start talking about superconductors, which is definitely a story for another day. In fact, it's a story for another course. Things always have at least a little tiny bit of internal resistance. Many times you can ignore it if you're not trying to be super precise about your calculations. But as you saw in the lab, when a battery gets old, typically the internal resistance becomes larger than it was when the battery was young. And so that's what we're dealing with here. You're only drawing 100 milliamps out of this old flashlight battery, but that's going to be enough to pull the voltage between the terminals down significantly. So once again, start out with a picture. Everything inside the little dashed box is the battery. The battery behaves as if it's a pure source of EMF at 1.5 volts. In series with a pure resistance that I'll call little r. We'll save capital R for the external, except I'm not actually going to use it. But if I wanted to have a letter for everything, big R would be the external resistor and little r would be the internal resistance. The notation is just because the internal resistance is usually small when it's not an old dead battery like this one. Anyhow, if you actually get a saw and cut into the battery and look, everything is actually all mixed up together. The resistance is the resistance of the same materials that are also producing the voltage. But as far as how it behaves as if you had a resistor in series with a pure voltage source, pure EMF. Outside the battery, we've got 10 ohms. Just like in the previous question, current flows from plus to minus. And the question tells us it's 1/10 of an amp. It's just like last fall when you have to remember to convert centimeters to meters or grams to kilograms for purposes of calculations. If you want the units to work out properly, you have to convert milliamps to amps or millivolts to volts, or, you know, that sort of thing. So part A, the internal resistance. Well, I'm going to write what amounts to the same loop equation that I had in number 2. If I go around this loop starting in the lower left-hand corner and go from there up toward the battery, I'll go up 1.5 volts as I cross the battery, and then down I times R as I cross this resistor, and down I times R as I cross that resistor, and from there you can get back to the starting point. So plus 1.5, the voltage of the battery, the voltage across the internal resistor, remember, Kirchhoff's loop rule is about voltages. It says the summation of the voltages around a closed loop is 0. So each term should be a voltage. The voltage across a resistor is given by Ohm's law, I times R. Sometimes I see people write these equations and they'll just have the 0.1 amps without the R, or they'll just have the 10 ohms without the I, or something like that. Each term is a voltage. So I times R for this resistor, and then I times R for that resistor. Summation of the voltages is 0. Well, the only unknown in that equation is the internal resistance, which is what the question asked for. So we've got 1.5 minus 0.1 R minus 1 times 10 is 1.0, then 1.5 minus 1.0 is 0.5, and I also added the 0.1 R to both sides, and finally you divide. So the internal resistance is 5 ohms. Part B, the terminal potential, meaning if you put a meter on here and measured the voltage between the terminals of the battery, how many volts would that be? Well, from one terminal to the other, that's the EMF minus what was lost on the internal resistance. Okay, as you go from one side of the battery to the other, that's these two terms right here. All of that's inside the battery. So part B, the voltage between the terminals of the battery is E minus IR. The EMF is 1.5 volts. I is 0.1 of an amp. And we now know the internal resistance is 5 ohms. So with this relatively small load on it, this supposedly 1.5 volt battery actually only has 1 volt between its terminals. And I guess that would be the reason that you need the EMF terminology. If you just say the voltage of the battery, well, are you talking about the 1.5, or are you talking about the 1.0 that you've actually got at the moment? EMF means the voltage under no load conditions, as I think I've already said before. If the battery is just sitting on a shelf, not connected to anything, so that the current is zero, then the EMF is the same as the terminal potential. Looks like it's time for the next page. Number 4. Kind of similar to number 2, except I took out the word series and put in the word parallel instead, which actually makes the question more complicated. So now we're talking about a circuit that has more than one loop in it. Again, we're going to need a picture to label stuff on. And just to generally help visualize what you're doing. 1.5 volt EMF. So 2 resistors in parallel. The other thing you want to label before you start flinging equations around is the currents. In a circuit with more than one loop, there are different currents in different parts of the circuit. Again, the current, the amps in other words, means the rate of flow. Coulombs per second through a wire, like how many cars per hour down a road. Well, if you've got maybe 50 cars per hour going down this road here, you get to this intersection. Some of the cars go straight, some of the cars turn right. So if you've got 50 cars per hour here, you might have 20 cars per hour here and 30 cars per hour there. Different rates of flow in different parts of the circuit. So you can't just label it I, like I did in the previous examples. You have to distinguish I1, I2, I3, or if you don't like subscripts, call them X, Y, and Z, or A, B, and C, or something like that. I've always been tempted to do a problem where I called the variables Bob, George, and Alice. Or you can do that too. Whatever it is, you have to give them different names. What I did is I said that the current through R1 is I1, which would be the same on both sides of the resistor. Again, it's the rate of flow. If you've got 30 cars per hour going here, you've got to have 30 cars per hour there. There's nowhere in between for any of them to turn off. And the current through resistor number 2 I thought I2 was an appropriate name for that. So the current flowing from the battery, which is the thing the question actually asks for, that one's going to be I3. So pick a loop. How do you know which one to pick? Well, if you've done this for a while, you can look at it and say, if I use this loop, that'll give me a simpler equation than that loop. But if you haven't done this for a while and don't notice anything like that, really, there aren't that many loops. Just start writing equations, and sooner or later, you're going to bumble into something that works. So let's not, sometimes there's something to be said for trial and error. Insight is better, but if you can't manage that, sometimes trial and error gets you where you need to go. So for my first loop, I thought I'd go around the left-hand half picture. Kind of like that. If I can get all this at the same time. So I started down here in the bottom left-hand corner. And you follow the wires. The first thing that you get to is the battery. You go from low to high, negative to positive. So that is an increase. That term is positive. Then you follow along the wire. No change in voltage, no change in voltage, no change in voltage. I get to the corner here and I take a right turn. Go down this wire, still no change in voltage. And then I come to resistor number 1. And I'm going from the upstream end to the downstream end. And that is a decrease in potential. So that gets a minus sign. And the voltage across a resistor is given by Ohm's law. I1 times R1. From there, no change, no change, no change, and I'm back to my starting point. So those two voltages have to add up to 0. Therefore, I1 equals E over R1. I have numbers for both of those things. Too bad the question asked for I3. Well, let's try again. For the next loop, I'm just going to go around the outside perimeter of the picture. Kind of like that. Following the wires, actually. I drew it out there where there was space to draw something, but the idea is I'm following the wires. So I start here, up 1.5 volts. So loop 2. E minus, well, I've gotten this far. I've gone up E volts. No change, no change, no change, no change, no change. I get to here, and I drop I2 times R2. So I2 is equal to E over R2. Now, if I wanted to make it a more elaborate version of the same kind of problem, maybe you can see if there was 17 resistors instead of 2 of them, there'd be another one here and another one here and another one here. And I would just keep going further out each time I wrote another loop equation. And I'd get that I3 equals E over R3 and I4 equals E over R4 and so on. Well, I still don't have I3. I've got both the other currents. Doing yet another loop equation is not going to be helpful, okay? You might be thinking, well, we haven't done the right-hand half of the picture yet, but that equation would not be independent of the two that I've already written, by which I mean you'll get an equation that I could derive from these two by substituting the one into the other and manipulating it around a little bit, okay? You can tell that by looking at the picture just from the fact that this loop over here doesn't cover any new territory that wasn't part of one of the loops I've already done. So we've learned everything that it's possible to learn from the loop rule. But remember, it's Kirchhoff's two laws. There's also the point rule. Let's apply the point rule right there. I thought point P might be kind of a catchy name for that point. The point rule is about current. Total current flowing toward that point equals total current flowing away from that point. What flows toward it is I3. I3 flows toward it, and I2 and I1, well, you know, it's like cars, like I was talking about before. 50 cars per hour here, 30 cars per hour there, 20 cars per hour there. 30 plus 20 has to equal 50 unless somebody's selling cars on that corner, okay? So it's the same thing with the amps. The rate that charge flows in has to equal the rate that charge flows out. I3 equals I1 plus I2. Substitute in the thing that I1 equals for I1, substitute in the thing that I2 equals for I2. And once you've got that written down in front of you, you notice that the EMF, the script E, is a common factor, and you could factor that out. And here's where I've demonstrated the formula for resistors in parallel. If it was just one resistor, you'd have I equals E over R. So that equivalent resistor, or 1 over that equivalent resistance, is equal to 1 over R1 plus 1 over R2. And if there'd been 17 resistors instead of 2 of them, it would keep going, 1 over R3, 1 over R4, and so on. So that's where that comes from. Filling in the numbers for this specific example, we've got 1.5 volts equals 1 over 10 ohms plus 1 over 20 ohms, 0.1 plus 0.05 adds up to 0.15 times the 1.5 volts, 0.225 of an amp. And we've got time for at least one more of these. 5. Well, as I said a while ago, you can't always just solve the problem by thinking of equivalent resistance. Yeah, this one you could. The earlier ones I did, you could. But now, this one here, number 5, the circuit's got 3 batteries in it instead of 1. So you can't just ask yourself, what's the effective resistance across the battery? You got 3 of them. So the only way you're going to get the answers out of this is by using Kirchhoff's laws directly, rather than using these rules for resistors that are derivable from Kirchhoff's laws. But as far as how you do this using Kirchhoff's laws, it doesn't look terribly different than the way I just did number 4. It's just that instead of having nothing but resistors over here, you've got a couple of batteries stuck in as well, which adds a couple of terms here and there to the equations, but it's a fairly similar kind of thing. So a picture that I can label stuff on. If it was a quiz, you'd probably just label stuff on the picture that came with the question. We've got 5 ohms, we've got 2 volts. In the middle of the picture, we've got 1 volt and 20 ohms. Over here, no resistor, just a 3-volt battery. Or maybe it's a power supply, something like that. Find the current through each battery. So it's a question with 3 answers. Just like in number 4, I need to give the currents in different parts of the circuit different names. So over here, thought I'd call that I1. And now, as for the direction the current flows, I mean, you need to have a direction for the current so you know where you should be using minus signs and where you should be using plus signs. Current flows from high to low through a resistor. You got to have a direction for the current to know which end is high and which end is low. When there's only 1 battery in the circuit, it's obvious. The current flows out of the plus side and into the minus side. When you've got 3 batteries, some of which are working against each other, it may not be so obvious. In a case like that, the thing to do is guess. Probably don't need to tell you that twice. That's a fine, long-standing tradition among students. When you don't know, guess. But unlike a multiple choice test where you more likely than not are not going to get anything out of guessing, just the wrong answer, in this case, guessing is harmless. If I1 in fact flows in the other direction, all that happens is when you solve for I1, you get a negative number instead of a positive number. Well, that still ends up telling you everything you wanted to know. And the only way you get in trouble is if you get partway through the problem, and let's say you calculate I1 and it comes out negative. Oh, I see now it goes the other way. And then you go to write, then you write your next equation under the assumption it goes the other way. Now you've built in a contradiction between the equations in your system of equations. So once you make a choice, stick with it, okay? Once you've drawn the arrow on the picture, don't go turning it around halfway through solving the problem. That will get you the wrong answer. But actually, the way I'm going to do this, we will get some negative answers. So just to show you what happens. So a perfectly reasonable thing might be for somebody to say, current flows from plus to minus. So I'll have I1 coming out of the plus side of this one. Current flows from plus to minus. So I'll have I2 coming out of the positive side of that one. And again, current flows from plus to minus. So I'll show the third current coming out of positive and going into negative on that one. And if you think about the point rule, you can see right now I've done something wrong because I've got all three currents flowing into that point and nothing flowing out. And that's not really going to happen. But like I said, it'll be fine. If it's not obvious which way the current flows, just guess. For my first loop, I went around the left-hand portion like this. So for no particularly good reason, I started here. And first thing that happens is you cross the battery, going from the low side to the high side, increase of 2 volts, plus 2 volts. Next, the 5 ohm resistor. Cross that going from the upstream end to the downstream end. That's a decrease. Current flows downhill. Voltage across a resistor equals I times R. This up here, so it's not going to come into this. So after crossing that resistor, I go along this wire, and I go down the center. This time I'm swimming upstream. I want to think of myself as a little microscopic charged person swimming around inside the wires. I'm going from the downstream end to the upstream end. That's an increase in voltage. And again, Ohm's law tells you how many volts you have across the resistor. The current in this resistor is I2. Next, I go from high to low across this battery. That's a decrease, 1 volt. And from there, I can get back to where I started. So those 4 terms have to add up to 0. Well, I can simplify that a little bit, but I've got one term with 2 variables in it. 2 minus 1 gives me 1. Worst case scenario for a problem like this one, and I think this does come up in at least one of the homework problems, you end up with a system of 3 equations and 3 unknowns, and have to apply the methods for solving a system of equations. This isn't going to be quite that bad, but we can't solve this yet. So just hang on to it. It'll turn out to be useful later. In the meantime, for my next loop, I'm going to go around the right-hand half of the picture, sort of like that. So I started down here. And the first thing I encounter is this 1 volt battery. I go from the low to the high side. That's an increase. Then the loop takes me from the high end to the low end of this resistor. So that's a decrease. Minus I2 times 20 ohms. Along there. I get over here, I go from the high to the low side of the 3 volts. That's a decrease. Plus and minus signs are a great way to lose some credit when there's a problem like this on a test. Increases are positive. This over here is a decrease. I'm going from the high to the low side, so that's negative. From there, I can get back to, oh, got to write down the 3. From there, I can get back to my starting point. Oh, well, should have gone with this equation in the first place. It's only got 1 variable in it. So 1 minus 3 gives you -2. I'll add the 20 I2 to both sides. Divide both sides by 20. So it turns out I guessed wrong about I2. The direction is opposite of that on the diagram. Got my arrows pointing the wrong way. Now that I have a number for I2, this equation that I circled back over here, I can stick in that number for I2 and I'll get I1. So it said 1 equals 5I1 minus 20I2, where I2 is -0.1. No, that's got a little carried away there. Right, okay. That's what's in the circle. Except I filled in -1 for I2. Right. So we've got minus cancels minus. 20 times 0.1 is 2. Subtract that from both sides. Well, I didn't do very well at all guessing the directions, did I? That one also turns out to have a direction opposite of that on the diagram. We have to finish up with the point rule. There's no territory left that hasn't been covered by one loop or the other, so we can't learn anything more from the loop rule. But if you you consider point P up here, this is on the next page. Total out equals total in. And again, stick with the choices you made. Don't turn anything around now that you know they actually flow the other way. What you showed on your picture is that nothing flows out. And I1, I2, and I3 all flow in. So 0 equals negative 0.2 plus negative 0.1 plus I3. I3 is 0.3 of an amp. And as Porky Pig always said at the end of the cartoon, that's all, folks. Except he said it cuter than that.